Okay, welcome to the next edition of the New York Combinatorics Seminar. We've got Rafael S. González D'León, who's going to tell us about Whitney numbers.
Thank you. Do you have to press again?
I think I clicked it, so see if it worked.
Yeah, it worked perfect.
Okay, good.
Okay. Thank you so much. Thank you so much for the invitation, the organizers of the seminar, and it's my first time here giving a talk in New York, actually. So it's very exciting for me. Also, we are beside the Empire State. Oh, I can see almost from the top. Wow, this is an amazing location. So I want to tell you about winning numbers today. So the title of my talk is on winning numbers of the first and second kind, or is it the other way around? Let's see. So this is the things that I'm gonna tell you are mostly joint work with Josh Hallam, that is my collaborator, but involve students that we have had, or I have had. Yeison Quiceno, he was at Universidad Nacional de Colombia, and then he moved to University of Florida. Andrés Molina was a Javeriana. I'm Colombian, by the way. I used to work in Colombia a few years ago, and they were students in Colombia. And José Samper, that is also a Colombian, but he is in Universidad Católica in Chile. So at the end, we have some ideas that involve José Samper, and I'm going to communicate to you these ideas as well. Okay. So let me start with a preamble. This is a graph. I'm very sure people are familiar with graphs. So we have vertices and relations between the vertices that are edges. The vertices have numbers. And actually, we're going to talk about colorings of the graph. And as mathematicians, colors are also numbers. So the important thing is a proper coloring. Sorry, I want to check, is everyone online seeing, listen to me well and seeing the presentation okay? Okay, thank you. Thank you so much.
Yes. Yeah.
Thank you. So in particular here, these two vertices are color 23, or whatever color is this. There is no edge between them, then they are allowed to have this color. If there was an edge between 1 and 3, I could not have these two color 23. So basically, this is what we call a proper coloring. So no edge can be monochromatic. Okay. This is just a preamble. It's kind of to put you in context of what I'm going to talk about. So the chromatic polynomial, basically, I give you a palette of X colors, and you are going to decide in how many ways you can properly color your graph with that X colors. It turns out this was started by Birkhoff in 1912. It turns out that this is a polynomial. Let's see an example of this. I have the path graph. If I have X colors, there is X options for me to color one. And then when I go to color two, I have used one color and I am blocked by one. So I can only have X minus one. And then the same happened with three. So I have X minus one, X minus one. That happens to be a polynomial. Okay. In the general case, it's not as trivial to find out this is a polynomial, but there is a way recursively to prove that actually this is always a polynomial, and this is why it's called the chromatic polynomial. So this is an algebraic device that had been used in graph theory originally to try to prove things related with the four-color theorem, but then later it has an interest in itself. Let's do another example. This is the example that I'm going to be using, the complicated example that I'm going to be using in the talk. I have X options for node 1. So we start X. For node 2, now we have X minus 1. And node 3, we have X minus 2 because it's blocked by 1 and 2. And this is a polynomial. Okay. In this talk, I want you to concentrate in these numbers, 1, minus 3, and 2. And for reasons that I'm not going to describe too deeply, these signs are always alternating. So there is no information on the sign. So forget about the sign. And actually, we are only care by 1, 3, and 2. Okay. So this is always an alternating sum. So just concentrate in 1, 3, and 2. So there are two interesting properties that these sequences of positive numbers can have. People are interested in this for various reasons. One is unimodality. So basically, if my sequence weakly go up and then weakly go down, and you only have one mode. So this sequence, very tiny example that we are visiting, is one of those. I go 1 up to 3, then down to 2. So this sequence is unimodal. There is also log concavity. If all the numbers are positive, this is a stronger property that basically I step in one number of my sequence, I square and I compare with the product of my neighbors, and I have to be larger. This is called log concavity. So the only non-trivial thing to check here, imagine that there were zeros here and zeros there, is 3 squared is greater than 1 times 2. Okay. So this is also a log concave sequence, and as I mentioned, this is a stronger property because log concave sequence of positive numbers are unimodal. So the context, some of you might have heard about this Reed and Hogarth conjecture, is that actually this thing that I did worked for any graph. Yeah, so there was a conjecture for very long. The absolute value, so forget the signs, of the chromatic polynomial as a sequence form a log concave sequence. And yeah, so this is kind of the preliminary context. This is how it relates to graph theory. I'm going to talk about other objects. These are my usual suspects in my work, and I work in something that is called posets, partially ordered sets. So my usual suspect is like, there is some poset somewhere. Here is the poset. So a poset is a set with a relation that is reflexive, transitive, and antisymmetric. Just to include something light in the talk, let me say that reflexive, I remember reflexivity by I am my own friend. Transitivity then is like friends of my friends are my friends.
Well, I'm sure.
Yeah. And what about the antisymmetry? My only true friend is myself. Yeah. If I'm related to Y and Y is related to me, is me. Maybe it could be antisocial, the antisocial type of relation. But a poset, like a finite poset, look like this. This is the Hasse diagram of a finite poset. So in particular, I'm just illustrating the covering relation. There is no other element between these two, so this is why I express a line here. And this poset has also other properties. It has a bottom, a unique minimal element. It also is organized by floors. We call this type of posets graded. Okay. It also has a top, but we don't need a top for the top. So in this talk, we have posets that have some bottom element, and they are organized by floors. So they are graded. We are going to use the grading for this. And I'm going to play in this poset a recursive game. This is the game of the Möbius function. So how the Möbius function game starts, I am in the bottom and I put a 1. And every time I do an interval, it needs to add up to 0. So if this is 1, what is the value of this one? Minus 1. Because this interval here up to the bottom needs to add up to 0. I already have a 1, so this is minus 1. The same way, this is minus 1 and minus 1. What is the value in the top? 2. Yeah? Because 2 and 1 is 3, and I have minus 3, it up to 0. So these are the Möbius values. So again, to find the Möbius values, I need to do this recursive game in the poset. So let's say to find Möbius numbers is already non-trivial. And since I have floors, I'm going to start adding these Möbius numbers by floor. I have a 1, I have a minus 3, and I have a 2. And we call these the Whitney numbers of the first kind. Okay? These are the Whitney numbers of the first kind. Do we find something special of these Whitney numbers? It's the only example that we have in the talk. So 1, 3, 2. Yeah, even with sign, but 1, 3, 2, this is the important thing. So this is also always true. Whitney proved in 1932 that these coefficients of this poset is called the bond lattice of the graph. In this case, this is the poset of partitions. I didn't tell you, but this is the poset of partitions of a set. I have 3 blocks here, and when I merge 2 blocks, I go up. When I merge another 2 blocks, I go up. This is the poset of partitions. There are bell number many elements in this poset. So what we need to say is like, hey, actually, I can build a poset of partitions out of any graph. And when I look at the Whitney numbers of the first kind, these are the coefficients of the chromatic polynomial. This is kind of an amazing result. It moved this graph theory question to posets. Okay. Are these posets interesting? Actually, yes. They are from a bigger family, the family of geometric lattices, or as other people know them, as simple matroids. They are the same as the the lattice of closed sets of simple matrix. So basically, this said that this problem in graph theory belongs actually a little bit more general to geometric lattices of matrix. And that conjecture of Reed and Hogarth was generalized by Rota, actually Heron and Welsh. Some people call it the Rota-Welsh conjecture, that this is actually true. We need numbers of the first kind. If I don't care about the sign, they are log concave for any geometric lattice. If someone proved this conjecture, then it will conclude the previous theorem, the previous conjecture. And this is actually now a theorem. It's a celebrated theorem by Adi Prasito, Hu, and Katz, that for any geometric lattice, this is actually true. Okay, so this sequence is log concave. So this also concluded the Reed-Hogarth conjecture. The proof of this was not simple. Actually, all the techniques that developed awarded Jung Hu the Fields medals in mathematics. So, so they are highly non-trivial. They use what is called a combinatorial version of Hodge theory, and then they use the Hard-Lefschetz theorem. And in my line of work, and in particular the things that I look, if I look at something that's called Hard-Lefschetz, I conclude that is hard for some reason. So it's hard. Okay, it's not a trivial thing. There is a Fields medal in the middle for some reason. So in this talk, I don't want to tell you about this Hodge theory and the hard thing. I'm actually want to tell you about a simpler set of Whitney numbers. Okay, simpler set. What would be something simpler to do in this poset? So for me as a combinatorialist, I already have a description of these elements. So I'm just gonna count by floor how many elements do I have. So I have 1, I have 3, and I have 1. Okay, these are also Whitney numbers. These are the Whitney numbers of the second kind. The easiest are of the second kind for some reason, but these are the Whitney numbers of the second kind. And so we have Whitney numbers of the first and second kind. Let me show you another poset just to give you another example. Without being too descriptive of this poset, this is called the poset of increasing spanning forest. They are all spanning forests, but in particular, the roots are the minimal elements. So this is the root of this tree, and this is the root of this tree. And the way I go back up is I take 2 trees, I join it by the minimal roots and choose the smallest. So for example, from these 2, if I join these 2 trees by the minimal roots and then I choose the smallest, I go all the way up to there. This is this poset. It's a different poset. I'm gonna play the same game. Maybe use numbers. 1 minus 1 minus 1 minus 1. That one over there is 1. Yeah, because I have minus 2, 1, so I need a 1 there. What about this one over here? 0. Because in this interval here, I'm already failing a little bit with this mouse, but in this interval here, I already have 1 minus 1, so then this has to be 0. Okay? And same game, we need numbers of the first kind and of the second kind. I compute it and I put it in this table. So they are here. Here are the previous of my previous poset. Is there anything that we notice from these 2 tables?
Symmetries?
Oh, there are also some symmetries up and down in this one, but let's say these are the first and second kind of the poset of partition. These are the first and second kind of the increasing spanning forest poset. They are flipped. Okay, so this is kind of the first observation that we landed to, like, oh, they were the same. And like, no, wait, actually, they have been flipped. Okay. And we call this, we saw this and like, oh, there might be dual of some sense. We call it Whitney duals. So with my collaborator, we say 2 posets are Whitney dual if this phenomena happen. They are graded, they have a bottom, and then when I look at the Whitney numbers of the first and second kind in absolute values, because there will be some signs involved in the first kind, they're actually the same, flipped. Okay, so in particular, the poset of partition and the poset of increasing forest are Whitney duals to each other. And we kind of went and proved this just by computing. You can prove this just by computing the Whitney numbers of the first kind and second kind if you can. And in this case, the first example that we did this. But then we open this question about what other posets have Whitney duals. This is the most classical of the posets. All the posets at the end reduce somehow to this one, is the Boolean algebra, poset of subsets. Here, the Möbius values are either 1 or -1, independent of the Floris design. And so then basically, the Whitney numbers of the first and second kinds, modulo sign, they are the same. So this is kind of a Whitney self-dual. And this, actually, there is a whole family of them that are called Eulerian posets. They have this, the Whitney number, the Möbius numbers are -1 or 1. We always need to play this recursive game, but in this recursive game here, we give us 1 or -1. We add up by levels. The only thing that differs is sign. So these Eulerian posets are all Whitney self-dual. Great. We have now two examples, Eulerian posets and this example that I gave you before. This is not a trivial property. Actually, let's go to another very trivial poset, a chain. Chain doesn't have Whitney duals when the length is already more than 2, because as we saw before, that number has to be 0. And if I had a Whitney dual, it means that I don't have elements at some level, but I have Whitney numbers. So it doesn't work. So this trivially fails, but there are more interesting examples that they fail. In particular, when you have zeros in the Möbius numbers, it's not always that it fails, but it's very likely to fail to have a dual, okay? So this is not a non-trivial property. So Josh and I, we were working in this, like, how do we get to study this property? And we were both graduate students at the time. Just gonna look at my clock, yeah. And we decided to try to construct Whitney duals from other posets. What techniques we were using? So my PhD thesis is about edge labelings. Josh's PhD thesis is about quotient posets, and somehow we met in a conference, and there were the two techniques that it occurred to us, and they worked. So I'm going to tell you how to construct these Whitney duals. So the first thing is I'm going to tell you about edge labelings. So what is an edge labeling? Basically, take another poset with your labels. So you want labels, but the labels have ordered themselves, and you want to put in all of these edges of this Hasse diagram, you want to put some labels. That's an edge labeling, okay? This is the poset that I'm using here, lexicographic order in these pairs. For this talk, actually, it's not too relevant to see what is this label, but I'm going to tell you. Every block has a minimal element. When I merge them, I just put the two minimal elements in order. This is what I'm doing in this particular example. But for the talk, it's not that relevant if this label sounds confusing. It's just a number. An element, sorry, an element of a poset. Okay. But here is too free of an object to be able to conclude anything. It needs some conditions to be able to conclude anything. So we are gonna say that a chain, a saturated chain, is increasing if when I'm going into these labels, I'm going up and up and up. And the other important chain is asymptotic or never increasing if I don't go up, I don't go up, I don't go up, and so on. Are there other chains? Yeah. Sometimes you can go up and then don't go up and then go up a little bit. We don't care about these other chains. We're going to care about these specials. The chain that I always increase, or the chains that I don't increase, I don't increase, and don't increase, and I don't increase. Don't increase in this case means it could be even unrelated, the label, because it's a poset. So let me show you again. Sorry. Let me show you again this. Notice this chain 1, 2 is less than 1, 3. So this is an increasing chain. 1, 3 is not less than 1, 2. So this is a non-increasing. So it's an asymptotic. And this one here is also an asymptotic. This is a very small example. So I only have an increasing and two asymptotic chains. Okay. In a general poset, I have the increasing, some asymptotic, some increasing at some point, and asymptotic in another part. We don't care about those. Okay. So why are these conditions relevant? Because Stanley defined this type of labeling. He used to call it R labeling, and we are putting an E because edge, and there are other type of labeling that generalize this. So what is an ER labeling? An ER labeling is if you can put a labeling on the edges of your poset such that for every element there is for every interval, really, there is always a unique increasing chain, a unique increasing chain. And the importance of this is this theorem of Stanley that says if you want to calculate the Möbius value and you find an ER labeling, then the way to calculate the Möbius value is by counting how many asymptote-free. So you need a unique increasing chain, but then the asymptote-free are the opposite friends. How many asymptote-free chains do you have in your interval? So let's see. I told you that this is an ER labeling here. There is a unique increasing chain, and there are two asymptote-free chains in this non-trivial interval. So it means that the Möbius value modulo design is 2, and this is what we saw before. Okay? Actually, you can also define a labeling dually to be R star. I could also require that for every interval, there is a unique, never increasing asymptote-free chain. And then the same statement of Stanley will tell you that to count the Möbius value, now you go to the increasing chains. So you see, there is certain type of duality here. The duality basically is telling me this. If I want to count Möbius numbers of the second kind, and I have an ER labeling, I can use this unique increasing that goes from bottom to there to count that element. So this give me the increasing chains, give me the Möbius values of the second kind. Sorry, the Whitney, the Whitney numbers of the second kind, thank you. The Möbius values are calculated by the asymptote-free chains according to Stanley's theorem. So the asymptote-free chains give me the Möbius value, the Whitney numbers of the second kind. But if I have this R star, where I don't require a unique increasing, but a unique never increasing, the things flip. So, and let me just show you again this. These are the two posets that I showed you before. This labeling here is an ER, and this labeling here is an ER star. Notice there are two non-trivial intervals here, and in these two non-trivial intervals, there is a unique, so in this one here and in that one here, there is a unique never increasing chain. In this case is 1, 3, 1, 2, and in this case, the only chain that we have is non-increasing. So what are the Möbius values there? Count the increasing. How many increases I have in this interval? 1. Möbius value over there was 1. How many increasing I have in this interval? None. So this is why we had a 0 there. You see? Okay. So this is how we are going to use labelings to be able to try to flip Whitney numbers of first and second kind. Okay? Question so far? Yeah.
Just curious, you ever label a poset with itself?
We
You ever label a poset with
This is an interesting question, but I have never studied that type of yet. But it sounds interesting. You could,
Yeah.
potentially you could. I mean, it's hard. Okay, what I would say is, when you're giving a talk on these things, it seems that the label is something like, oh, labelings. To find these labelings, I believe that it's kind of an art. it's very artistic. It's the thing that works for your objects and so on. And there are many, it's very often to find even articles where they try to make a labeling and all this. Oh yeah, of course, this is gonna, for this type of labeling, every interval needs to satisfy this. From the big one, the smaller one, yeah, every interval. So it's very hard it's actually a really hard job to find such a labeling. Yeah. So to answer your question, it is unlikely that the same poset labeling the same poset is gonna give you an ER label. Yeah. Okay. Cool. So I mentioned labelings. So this is labelings. So again, the preamble was about Whitney numbers of the first kind and second kind and graphs. Then I want to switch maybe Whitney numbers of the first and second kind. It seems that labeling is a way to do it. And so we define a family of labelings that now we call it Whitney labelings or EW labelings, where we have this property, but we need something else. And the main thing that we need, we call it the rank 2 switching property. I'm gonna describe. There is another injectivity condition that I put under the rug. All the examples that we have found have this injectivity condition, but it's important for the proof, and I don't think it's avoidable. But I'm not gonna tell you about this injectivity condition. It's an easy condition. But the rank 2 switching property is as follows. You go and look at small intervals of rank 2. If it's ER, it needs to have one chain, like this one, that is unique increasing. I want to ask for another chain that has the opposite labels. You see, I have the 1, 2, 1, 3, that is my unique increasing. So I want to have the 1, 3, 1, 2. I want that. In some sense, I want to switch an increasing step into a non-increasing step uniquely. This is what I want to do. And then with this property, we are able to conclude this. If I have a graded poset, as the one that I show you there, with an EW labeling, actually we have a Whitney dual. And this thing is constructive. So doing certain operations that I'm going to show you, you can construct your Whitney dual. Okay, this is so let me show you how to construct it. Start with your poset. This is the poset of partitions. You're going to take all chains from the bottom. So this element is here. Then I take this chain, is here. Then I take the longest chain, is there, and by inclusion. So this is less than this, is less than that. So this expands as a tree. The chain poset is like a tree. It's a tree. But then I want to start using quotient poset to quotient things, to identify things. And this is where the rank 2 switching property comes. That chain and that chain, I'm going to identify them because I can go from here to here by doing a rank 2 switch. So basically, I can turn an ascent into a non-ascent. So this is this, into a descent gradient. Okay. So these two chains are going to be identified. So I have these are in the top. I'm going to identify these two chains. These are the set of labels. And then I do a quotient. Does this poset look similar to the one before? It does, yeah? Actually, by not a coincidence, those labels there represent the edges on the trees that we had before, okay? And the next step that I have to do is to translate somehow this label into there. So now we have the same set of labels, but the end of the proof, this is very non-trivial. The paper is really long, by the way. In this case, it's a little bit easy because it's a chain that is labeling. The labels are totally ordered. But if you see, there is a bijection between the increasing chains from the bottom from here to here that preserves the labels. And in here, we have an EW label, sorry, an ER labeling, and there we have an ER star. So the same chains, but here Möbius numbers of the first kind are increasing, the second kind are ascent free. Here, the other way around. So this is the duality. Okay. So that's the poset that we get. So in other words, with this new type of labeling and our theorem, that poset ended up being constructed from the first poset. Okay. So this is kind of the main theorem that we have. So what questions now we attacked? Because we have only one example. Please stop me at any moment if I'm going too fast with this. Let me just do a kind of a summary. I started with graphs. I moved to posets. The posets have Whitney numbers of the first and second kind. People are very interested in the Whitney numbers of the first and second kind. We find other posets that switch the Whitney numbers of the first and second kind, and we develop a technique that allows to prove for certain posets that they actually have that friend. Okay, this is what we did. That technique is with labelings. We apply some quotients to reconstruct the second one, and this is our theorem.
So I'm guessing that there's a combinatorial reason why the pictures you had on the second one are the right dual. are there other good examples of these? What are some other pairs of things? Are there some nice combinatorics there?
Thank you for the question. This is the nice question because it's my next slide. Yes. So the question at this point is, okay, that was very combinatorial. There are forests that is very natural. Are there examples? So then we go and try to find examples of our theorem, okay? The first thing that we went, of course, was to geometric lattices. And Stanley has defined, actually that labeling that I showed you was a particular example of a labeling strategy that Stanley defined that are called minimal labelings. You take the atoms of your geometric lattice and always label with the minimal atom that take you up. This is kind of the strategy. So basically, for this talk, there is a strategy that Stanley defined for geometric lattices that give you R labelings. We prove that those have the rank to switching property and this injectivity condition. So all of them, all geometric lattices, have Whitney labelings. And these in particular are the labeling that Stanley already have defined. So using our theorem, we conclude that all geometric lattices have at least one Whitney dual with this construction. And those Whitney duals, so when we go, they all look similar to this one. They are all forests of certain type of trees, all forests. It is very common for the posets that have to do with partitions that the dual end up being forests of combinatorial objects. Okay? This is a very common. So far, every example, I'm going to tell you more examples, but so far, every example that we have is a very nice dual poset. It's a very nice, either new or not new, but very nice. So geometric lattices are Whitney dualizable. We can construct this. So in particular, we can make the Whitney numbers of the first kind, the Whitney numbers of the second kind of these other combinatorial posets. Okay, this is the conclusion. But there are more. There is a poset that is called the poset of non-crossing partition. Take the partitions that are non-crossing, that have non-crossing blocks. This is a lattice, but it's non-geometric. Stanley has already defined a labeling for this. And our labeling, we prove that this R labeling is actually also a Whitney labeling, an EW labeling. So we also have that this one is Whitney dualizable. The dual that we found that I didn't bring a picture because of a matter of time, but maybe I could say a little bit more of this, is a poset on Schroeder paths. So there is this family of combinatorial objects that are called Schroeder paths. They define now my levels in my dual, and there is a way to go from one Schroeder path to another one. Schroeder paths are lattice paths that have, let's say, imagine in a grid n by n, you can either go east, north, but also you can go diagonal. Okay, those are Schroeder paths. And the poset that we obtain, maybe, I mean, this won't be very good. People in this cannot be seen from the, okay. But let me just do, so for the people in the audience, I'm just doing a grid, and I'm gonna start with a shredded path that is just a diagonal in the grid. So the way to go up is just to try to push diagonal. So I can push the diagonal into this, but I could also push the diagonal into that one. So when I have a long diagonal, I can push just one level up in all the possible ways that they can do. That's the poset that we obtain. So it's a poset on shorter paths with that nice combinatorial rule. Okay, so non-crossing partitions are good examples of this. Is there any way to see if we have a question from the? I am the only one who have access, yeah?
There's someone on the.
There is something in the chat. Let me see.
Yeah, I think, oh, we have to bring the mouse back on. Yeah. stuck. It can't
Yeah.
exit that second screen, so I don't know.
Is there someone that could read the question in the chat?
Log into the Zoom, somebody's.
Yeah, I will continue. Yeah, I will continue.
Yes, there's a question in the chat.
Thank you.
By Anna Pan. Will some of those admitting ER labeling also admit an EL labeling ? Or if these posets are shellable ?
Thank you so much, Anna. So we don't require, for our construction, we don't require to be EL, so we don't require the lexicographic condition. However, all of these Stanley's labeling were EL labelings. And in the examples that we give for some other posets that I'm going to mention in a second, some of them are EL labelings and some of them are not. Okay, so basically, some of them are not EL labelings, but they are EW. And so far, we don't think also that we have the same algebraic conclusions or the same shellability conclusions with EW labelings that with EL labelings. We don't know, but I particularly don't think. I was trying to prove that EW labeling have the same conclusions. I haven't been able to do it. Yes, so some of them are EL labelings as well, some of them not, and you don't require lexicographic condition for this to work. Okay, thank you for the question. Okay, so I'm in the examples. I said all geometric lattices are in my pool. The lattice of no crossing partition, but there are more, are things that are even no lattices. So with Yeison, we started, there are some posets that are coming from operatic theory. So poset based on partitions with decorations, because basically you have these algebraic objects that combine elements called operats. And then what you do is now you take the blocks in your partition, you combine them, but basically decorating with the element that is operating between them. In my PhD thesis, I studied one of them that is called the poset of weighted partitions. It was introduced by Dotsenko and Koroshkin in relation with the operats of COM2 and Lie2. In particular, Lie2 is Lie algebras with two compatible brackets. And Chapoton and Valete have studied before a poset of pointed partitions related with the operats perm and pre-Lie. Okay, so basically there are these algebraic operats that you can construct posets with them. People have studied. I studied one with my advisor, one of them. And then we've tried to find labelings. I already have a labeling with Michel Vax for the weighted partitions. Yeison went and find one from the pointed partitions. Again, I tell you, this is not easy. He was doing his master's. And when we started the project, I kind of had an idea what the labeling will work. And we started with this, didn't work. And then he went into months of trying to get this artistic path that I tell, and he was able to come out with this. This is not highly non-trivial. So basically, he was able to construct a Whitney labeling for the poset of pointed partitions, and we prove that a labeling that was lexicographic, actually a EL labeling that we have for the poset of weighted partitions, was actually a Whitney labeling. These two posets that I'm not showing you because it's another picture, but these two posets are really, really interesting because we have already noticed since my PhD thesis that these two posets have the same Whitney numbers of first and second kind. So they are somehow Whitney twins. We are calling Whitney twins. The same Whitney numbers of the first, same Whitney numbers of the second. And now with this theory, with these two different labelings, we produce Whitney numbers of the second first, that are twisting, basically that flipping. So basically we have two posets that they have the same Whitney numbers of the first and second kind, and they have duals, and we prove that these duals are not isomorphic. So this is a very nice set of examples. But these two posets coming from operatic theory, they are Whitney twins. They have Whitney duals, non-isomorphic, so we have two other Whitney twins that are Whitney duals to these ones. This also tells us that this is very non-unique. Yeah, it's non-unique because we have multiple Whitney duals. So maybe the duality really is a duality of Whitney numbers, not the duality of the poset themselves. Okay? Does this make sense? Yeah. So this is the value. This is a recent paper. I mean, recently accepted paper. So you can find it in the archive, for example. So this shows you non-uniqueness. There is another one that shows you non-uniqueness. So with Andrés Molina, he was before at Pontificia Universidad Javeriana, where I was working there. He was an undergraduate. Now he's in Kansas U doing his PhD. We were always, Josh and I, we were always assuming for a wrong reason that when you take all of these atom orderings for the Stanley label, all of them will give you the same dual. I mean, I don't know what we were assuming this, but we were assuming this. For some reason, we convinced ourselves that for every geometric lattice, Stanley labeling give you many labelings. Just order the atoms in all the factorial ways that you can do. And we were assuming, for some reason, we convinced ourselves, oh yeah, there had to be some isomorphic because of blah. They are not. They are not. But it was wrong. And so with Andres, we started, he coded all of these with labelings and then constructed duals, and then all of these non-isomorphic things started appearing. I was like, what? They were supposed to be all isomorphic. No, they are not. So this gave us examples of multiplicity of Whitney duals. In particular, take for example the Fano matroid. The Fano matroid has 5 Whitney duals coming from atom ordering. So out of the all possible 7 factorial orderings, 5 non-isomorphic duals come up. If you take the non-Fano matrix, 42. And then we were seeing all of this multiplicity on the duals. We still don't know what those numbers mean.
Catalan.
But this one is Catalan, but then we don't know. We don't know. We haven't tried. Maybe we have actually tried another projective geometry, but we haven't seen the 14, I think. This 42, actually Catalan. This is true. This is what you're saying. Yeah, sorry. We also were playing this game that let me just not be abusive of the time. How much time do I have?
Oh, till 1.
Until 1. Okay, so I'm good. Yes, so no, this is perfect. So we start running examples to try to see how many classes do we get, basically to see if for any number we have that many classes. Yeah, so we have a matroid that gives us how many classes, and we still have holes. Like maybe 3 is one hole. So we have one matroid that has 1 dual, matroid that have 2 duals, matroid that have 4 duals, 5 duals, and so on. But we have some holes so far. We don't know if this is complete. This is another problem. I mean, maybe it's a made-up problem, but it's a problem. Okay. But we also started to see some matroids with unique. When you take all of these factorial EW labelings and construct the dual, they were all isomorphic. So we started seeing a lot of them. And we started observing that they were kind of uniform, all the uniforms are there, but then there were also direct sums of uniforms. And we were able to prove that. So actually we prove that if you have a direct sum of uniform matroids, then all of these factorial labelings give you the same dual. It doesn't mean that it's the only Whitney dual, because this is one strategy to construct Whitney duals with minimal labeling. They could potentially be another labeling to give you another dual. But from the minimal labelings, we only, for direct sum of uniforms, they only will give you 1. So far for us, this is also a conjecture that for all the data that we have observed, these are the only ones that appear to have. We still have not proved this other part. So basically, conjecturally, these are the only ones that have a unique class, but we don't know. So so I'm gonna start now jumping with some conjectures here. So this is one conjecture that Andres and I, and Josh also, and José Samper, we have been thinking about. So this is the first conjecture, and can someone read further questions in the chat? I will appreciate.
No further questions. in the
There are no
chat.
further questions. Okay.
Yeah.
Okay, so let me just, to close the session of today, I also want to say the following. So we have this strategy. I mean, there are a lot of questions here. One question that is really hard is, imagine that I give you two sequences of numbers. How likely is that you're gonna find a poset that the winning numbers of the first and second kind are gonna give you this? This is a really, really hard question, yeah? Now, imagine that you have a poset that has these sequences, and that there is this question that we were attacking. Can we find, are these sequences Whitney dualizable or not? Can we find another poset that flip? We have a technique that in a lot of families given, but we don't have like a full answer, yeah? But these techniques for a lot of posets that are out there in the literature is working. To be honest with you, we haven't explored even enough, because we went to, oh, what about this poset? They have labelings. Oh, actually, this happened to be Whitney labeling, so they have. So we immediately conclude that this is true. But also, this technique includes all geometric lattices that are of interest. Yeah. And not only that, is you have a geometric lattice, you have the Whitney numbers of the first kind that have been shown to be log concave. The second kind, no, they have not been shown to be log concave, but they are conjecturally log concave. And you can find another poset that is very combinatorial where these two things are switched. Okay, so we think that the technique of Whitney labelings could be fundamental of trying to find, let's say, strategies to prove the log concavity combinatorially. Okay, so this is one of the things that we are looking at right now. Can we use this technique to construct a dual, and in this dual try to prove something combinatorially? Yeah, this is one. But also, we have the geometric lattices that basically there are these nice theorems of log concavity for the Whitney numbers of the first kind. And then we have the non-crossing partitions. They also satisfy this. We numerically calculated. We have the poset of operatic partitions. They also satisfy this. So we have infinite families larger than the geometric lattices, where this thing is also true. So basically, we conjecture, or ask if you want, but this is our conjecture. So far, all the data point to this, that if you have a graded poset with a bottom and a Whitney labeling, a EW labeling, then actually the Whitney numbers of the first and of the second kind are log concave. Okay. Again, this has been proven for geometric lattices. Either the techniques that were for proving for geometric lattices will work, or something more combinatorially related to these duals could work. The nice thing about this conjecture of being true is that if this is true, this potentially could be also a technique to prove log concavity to some sequences. Yeah, like if you have a sequence that actually there is a poset that you already know that realize the sequence, and you can produce a Whitney labeling, then you get your log concavity result. I mean, this is too much to aim, but this is the conjecture that I'm proposing here. And there is another thing that was conjectured before for geometric lattices and was proven by Braden, Ho, Matern, Proudfoot, and Wang for matroids, or for geometric lattices. That is basically this top-heavy conjecture that if you look at the geometric lattice and you look at the level I and the level rank minus I, the rank minus I have more elements than the level I, so it's top-heavy. All of this, well, this is true for matroids, but all the other posets that I told you also satisfy this. So conjecturally, this could also be a technique. If this is true, this could be also a technique to prove top-heavy for some posets. Okay. And yeah, so I leave you with these conjectures. Gracias.
All right, any questions in person? Any questions on Zoom? Just speak up.
I think there must be one, but can someone read it?
No questions.
no
One
question.
person said that he had to leave early.
Okay.
Yeah, thank you for a wonderful talk. That was very nice. I'll be in touch with you. My area is Macoids.
Oh, okay. Thank you. Who's speaking? Sorry.
I'm Sandra Kingen.
Hi, Sandra. Thank you.
Yeah.
Okay, well, thank you again.
Thank you so much.